All right, here we go. So welcome back. What we're doing today is finishing up our discussion of vectors that we started on Tuesday. So in this lecture, we're just undergoing sort of a mathematical treatment of vectors. We're looking at this from a pure math perspective. But when we get to the next chapter, the lecture that we start next week, we'll start to see how this stuff applies to our physics equations. All right? But for now, it's just pure math. So what did we cover? We covered how to represent a vector on a graph. We covered the Cartesian form of a vector and the polar form of a vector. And what we're going to eventually get to today is how to actually calculate the sum of two vectors. Okay, so we showed how to do that just by making a drawing before, but by the end of today, we'll see how to actually calculate using numbers what the sum of two vectors is. Okay. So this is where we left off. What happens when you multiply a vector by a scalar? So remember, a vector is something that has a direction to it, and a scalar does not have a direction. It's just a pure number. So you might ask, like, okay, if I have some vector, what happens when a scalar gets multiplied in front of it? So the answer is pretty straightforward. If you take a vector and you multiply it by a scalar, you still have a vector that's pointing in the same direction as it was pointing before. It just gets scaled up or scaled down, okay? So let's take this as our example. This is vector A, okay? So it's pointing into the first quadrant, and we can see what its length is just based on the picture. Now, if I were to take this and multiply it by a scalar of, let's say, a half, I would still end up with a vector pointing in the same direction, but its magnitude just got cut in half. So that scalar I multiplied by it shrinks it by a factor of half, right? But if I were to take, let's say, a negative scalar, let's say minus 2 times a, the negative scalar actually flips the direction around. Okay, so it's pointing in the opposite direction as it was pointing before, and this factor of 2 means we double the length. Okay, so that's what happens when you multiply a vector by a scalar. Does that make sense? So hopefully you can see how this would generalize to any kind of scalar we throw in front of the vector. So here, just a question to get you thinking about this. So suppose we have vector A. Let's say it has a magnitude of 6 and a direction of 45 degrees. The question here is, what is the direction of the vector minus 3a? So we get this new vector when we multiply by minus 3, right? What direction is that pointing in? If we were to give it as an angle. So if you can't immediately see it, just try drawing it out, and it should be pretty clear from your drawing which way the vector is pointing. So make that drawing on your paper, take a few minutes, take a minute to do this, and then we'll look at it together, okay? All right, do you see what it is? All right, what's the answer?
6.
Yeah, it's got to be pointing at 225 degrees. So let's just make the drawing. So some of you did this in your head. This is the drawing I was suggesting you make, right? Vector A, let's put it in the xy plane. And if we say the angle is 45 degrees, what we mean is it's 45 degrees going off the x-axis counterclockwise. So there's A. Okay, if I take this vector and I multiply it by a negative scalar, I automatically know that the direction gets flipped around. So it's pointing in the opposite direction, down here somewhere. But since the scalar is minus 3, that means I'm going to be tripling the length. So if I want to indicate that I'm tripling the length, I'll draw it 3 times as long like this. And there's my vector minus 3a. Okay? And of course, if we were to specify the direction of this vector, it would still be measured off the x-axis. So it's really just like adding 180 to what we had before, right? 180 degrees plus 45, 225. So that's why the answer is 225. All right, pretty straightforward. Good on this? Okay. So that takes us to subtracting vectors, right? We covered last time how to draw a diagram that shows the addition of two vectors. Okay? So now we want to know how do we make a diagram that shows one vector being subtracted from another. And actually, it's just the same exact rule that we used last time. Remember this tip to tail method? Okay, from 2 days ago, we learned about the tip to tail method. We're actually still going to use that. We're just going to think about subtraction as adding a negative. Okay, so if we know how to add vectors, subtraction is just adding the negative of a vector. So let me show you what I mean here. So in this example, we have vector A going straight to the right. And vector B is kind of like this in the first quadrant, okay? But I don't want to do A plus B. What I want to do is A minus B, okay? So I can think of A minus B as just A plus negative B, right? That's the same thing. And we know how to treat the negative of a vector. Minus B is just vector B, but flipped around 180 degrees, okay? So thinking about it this way, I'll take vector A, and I'll draw it first, and then I'll take vector minus B. So this is not vector B, this is minus B because it's flipped around, okay? And by adding A to minus B, I've done the subtraction that I'm trying to do, okay? So the resultant vector, as always, the vector we end up with after we do this operation, it starts at the beginning of the first vector, and then it ends at the end of the last vector. Okay, so you can handle vector addition using the tip to tail method, and you can handle vector subtraction as well. Okay, because you just flip a vector around if you're trying to subtract it. Make sense? Okay. And of course, this comes from the idea of multiplying by a negative scalar.
Is it only B that gets flipped around?
Well, yeah, if we're trying to do A minus B, it's only B that has the negative sign in front of it. If we were doing B minus A, then yeah, we'd flip A around. Yeah. So it all depends on exactly what's going on. But hopefully you see the process. Okay? Okay, so now what we're going to do is move from the graphical method of adding vectors, which involves drawing the vectors on a diagram and showing them connected tip to tail. And we're going to move on to the algebraic method. So this just involves pure numbers. We actually don't even need to draw a diagram to do it this way. And usually, if you're trying to make a quick calculation, this is the way you're going to go. So let's now talk about how this works. All right, so let's say we have two vectors we're trying to add together, and we're just going to generically call those vectors A and B. And the resultant vector I get is going to be called R. Okay, so I'm trying to basically figure out what R is, given A and B. So the first thing that I'll do is I'll take each one of these vectors and break them into X and Y components. So the exact numbers that go into this will depend on the specific situation you're in. So I'm just going to write it as AX, AY for the components of A, and then BX, BY for the components of B. So I'm just generically writing each one of these in component form. You remember how this looks? If I'm trying to write vector A in component form, it's AX times I hat plus AY times J hat. If I'm trying to write vector B in component form, it's BX times I hat plus BY times J hat, correct? That's just generically how it works. So all I'm going to do is take these expressions where everything is broken down by components and then put it into here. Okay, so here's what we have. When we add the vectors together, the resultant vector R is vector A, which is AX I hat plus AY J hat, plus vector B, which is BX I hat plus BY J hat. Okay? And the next thing we're going to do is pretty simple, okay? I have 4 different terms here, correct? But notice how 2 of my terms have an I hat multiplying it, and then 2 of my terms have a J hat multiplying. So I'm just going to group them together according to whether there's an I hat or a J hat, okay? So, in other words, we're grouping the X and the Y components. So I can group together ax and bx because they're both multiplying I hat and write it as ax plus bx times unit vector I hat. And I can do the same thing for the y components. I can say we have ay plus by times j hat. And actually, we're pretty much done if you think about it, because that means for our resultant vector, whatever vector we end up with, it has an x component, which is just ax plus bx. So in other words, if I want to know what the x component of my vector that I end up with is, I just take the individual x components of the vectors that I'm adding together, and then adding those up, okay? Just adding the x components to get the final x component. And the same goes for the y component, right? This is the y component of my resultant vector, which I get just by adding the y components of my vectors that are going into it, okay? So in a nutshell, here's what we can say. The x and y components of my resultant vector are rx equals ax plus bx, ry equals ay plus by. But, you know, forget all this abstract notation. What is the takeaway point of this? If I want to add two vectors together, all you do is group the x components and add them. And then group the y components and add all of those together. Okay? And this doesn't just apply for adding two vectors, by the way. I could be adding any number of vectors together. Okay, if I were adding 100 vectors, I would add up 100 x components over here. And then I would add up 100 y components over here. You see what I mean? So it's completely general to any number of vectors. So we're going to see some examples of this just to make it absolutely clear. And I'll show you some useful methods to keep track of everything in your calculation. But this is the basic idea. We add by the components. So I want you to try this one out. We have vector A with an x component of -4 and a y component of 2. And then we have vector B, which has an x component of 1 and a y component of 3. So first, what I want you to do is find the sum of A and B just in component form. So in other words, just give me the x component of that sum and the y component. But then after you've done that, figure out what the magnitude and the direction is for that resultant vector. Okay, so first step is just add them together, get the x and y components, and then once you have that, find the magnitude and direction. Okay, so see what you end up with, and then we'll go through it together. So that's the right set of components. So if you were to get the magnitude, you could just use the Pythagorean theorem on that. So like 3 squared plus 5 squared square root. And then you could use tangent to get the direction. Okay, so I see some people are starting to get this. Let's at least make sure we're on the same page as far as how to calculate the sum. And then we'll figure out how to turn that into a magnitude and direction, okay? So I'm going to show you sort of a way of organizing the work that I'm going to do a lot in this class. And hopefully this will help you when you see problems like this, especially when there are a lot of different vectors involved, okay? So here, vector A, if we're saying it has an x component of -4 and a y component of 2, we'll say it's -4 I hat plus 2 j hat, and then vector B, x component of 1, that's 1 I hat plus y component of 3, 3 j hat. Okay, and what we're calculating is the sum of these two vectors. So I'm going to call that R. So R is equal to A plus B. All right, so let me show you how to organize this on the page. First, I'll just write down vector A. So that's -4 I hat plus 2 j hat. But next, I'm going to write vector B, but just below it on the next line. Okay, so that way, I'm adding to it 1.0 I hat plus 3 j hat. And the way I'm writing this, you see the x components line up. Okay, and if I had more than 2 vectors to add, I would just keep doing this. And so all the x components would line up, and it would be pretty clear I'm just adding down this line to get the total x component, right? And then same for the y component, right? I would just be adding up all these numbers. So I could do it for any number of vectors this way. But anyway, what I end up with is -3 I hat, and then plus 5 j hat, okay? So that would be the resultant vector in xy form. But how would I take this and then calculate a magnitude? Let me ask you that question. How would I take the magnitude of this vector? So yeah, so here, this is how it works. If I have a vector and I know its x and y components, I take the square root of x squared plus y squared, basically, which in this case means I'm taking the square root of -3 squared plus 5 squared. And what does this work out to? Yeah, it's like, it's about 5.8 when we round it to the right number of sig figs, 5.8. And then what can we say about the angle? Remember, we learned last time how to take a vector in xy form and convert it to a magnitude and direction. So for the magnitude, we use this, the Pythagorean theorem. For the direction, do you remember what we used? It was a tangent function, right? Let's just recall. Tangent of whatever angle this vector is pointing at would be ry divided by rx, correct? But we have to be a bit careful here, right? Look at this resultant vector we ended up with. What quadrant is that vector in? It's in quadrant 2, because I have a negative x component and I have a positive y component, right? So this is in quadrant 2, meaning when I actually calculate the angle, I take the inverse tangent of y over x, which is 5 over -3. But then, what do I do to that? I'm going to add 180. And what do I end up with? So if you punch into your calculator inverse tangent of 5 over -3, what's going to pop out is -59 degrees. And you can verify that. But we're going to add 180 as a correction, and we'll get 121 degrees, okay? So those are the answers. We end up with a vector, magnitude 5.8, direction 121 degrees. All right. Now, what I'm going to do next, we're pretty much done with the problem, but I just want to show you a way you can just check the work to see that it makes basic sense, okay? So I'm going to actually draw a rough sketch of the diagram which shows these two vectors added together, okay? So here we go. Vector A. Which quadrant is this vector pointing into? The one that has a -4 for the x component and 2 for the y component. That's pointing in the second quadrant, something like this. We agree? This is a rough sketch of where vector A is going. What about vector B? Which quadrant is that pointing into? Yeah, it's pointing into quadrant 1 because it has both positive x and y components. And it's a little bit shorter too. So again, I'm not drawing it exactly, but that's roughly speaking what A plus B looks like when we connect them tip to tail. So the resultant vector, according to my diagram, is pointing like this into the second quadrant. So that matches our result here. We did find that it ended up in the second quadrant. So this is just a sketch to just make sure that your calculation makes basic sense. In this case, the calculation is really easy, but in other cases, you might want to draw this diagram just to check your work, okay? Any questions? Okay. So let's talk a little bit more about these things called unit vectors, which we call I hat and j hat. And I just want to give you some sense as to why we actually use them. Okay? They're not just there for decoration. There's a real purpose to this, okay? So basically, unit vectors, you can think of them as the building blocks of all other vectors. So if I combine my unit vectors in just the right way, I can basically get to any vector I want. I can build up any vector I want from those unit vectors. And the way that actually works, if we want to get into specifics, is like this. So let's for now just focus on 2D vectors, which just have an x component and a y component. Okay? So if we just have a 2D vector, I can take any vector I want and express it as a vector that's going along the x-axis, added to another vector that's going along the y-axis. So if I just break my vector down into one that points straight along the x-axis and another that points straight along the y-axis, I'll get my final vector. And basically, the I hat unit vector points along the x-axis, the j hat unit vector points along the y-axis, so that's how it allows us to combine things in this way. So let me show you what I mean with an example, okay? If you don't see what I'm saying already, hopefully this example will make it clear. So the example I want to take is, let's say we have vector A, which is 4 times I hat minus 3 times j hat, okay? So what I want you to sort of see this as is we're adding this vector 4 I hat to this vector minus 3 j hat to get the vector we want, okay? And that's how we're building it up from the I hat and j hat components. Okay, so here's just a quick drawing of that. So if vector A is 4 I hat minus 3 j hat in our example, I'm just going to write that a slightly different way as 4 times I hat plus minus 3 j hat. And what I want you to imagine is these are two different vectors that we're adding tip to tail. Okay? Now, what does the vector 4 times I hat look like? Let's think about it. I hat is just a vector that points along the x-axis, right? And its length is 1. So if we multiply that by 4, that's a vector that's pointing along the x-axis, and now its length is 4, right? Okay, j hat, that points along the y-axis. But if we multiply it by minus 3, we flip it around, so it's pointing along the negative y-axis. And now its length is 3. Okay, so what happens when I draw those added together tip to tail? Well, 4 I hat is going to be pointing like this, and then minus 3j hat is going to be pointing down like this. And I'm meaning to show this having a length of 4 and this having a length of 3, okay? And then my resultant vector is what I get when I add these two component vectors together, okay? And of course, 4 and minus 3 are just arbitrary numbers I chose, right? If I change those numbers to something different, I can get to any vector I want within the xy plane, okay? So that's what I mean by I hat and j hat are sort of the building blocks of everything else. Make sense? All right, so they're not just there for decoration. Hopefully you see that. Okay. Do you remember this example? We have vector A with a magnitude of 15 kilometers in a direction of 15 degrees. We had vector B with a magnitude of 12 kilometers in a direction of 75 degrees. Vector R is the sum of A and B. So what we want to do here is find the magnitude and direction of that resultant vector. So remember, we did this last time, but we did it using graphical methods by just drawing a picture, right? This time I want you to try it out by actually making the calculation, okay? You guys see what I mean? Let's get started off on this one as a group, and then I'll, once we're about halfway through, I'll let you guys try it yourself, okay? But let me start you off like this. All right, so we have vector A, okay? And that has a magnitude of 15 kilometers. So we write the magnitude this way. Its direction, which I'll call theta A, is 15 degrees. So I don't have this vector in xy form, right? I have it as a magnitude and a direction. But if I'm going to actually add this together with another vector, I first want to break it down into xy form. So ax, do you remember what the formula for the x component of a vector is if we have the magnitude and the angle? We worked this out last time. So just go back to your notes and see what it was. Yeah, so if I want the x component of vector A, that's the magnitude of A times cosine of the angle for vector A. So we can actually just directly calculate this. So get your calculator out. We have 15 kilometers for the magnitude, and then we have cosine of 15 degrees for the direction. What does that work out to? Yeah, so I'm going to just say that's 14.5 kilometers, but we'll keep 2 sig figs on that. So the bar is telling us to keep 2 sig figs at the end of this, okay? What about AY? What's the formula for that?
It's A times sine of theta.
Yep, so if I want the y component, I will take the sine of the angle theta instead of the cosine. So I'll have 15 kilometers, sine 15 degrees, and what will that give me?
3.9.
Yeah, it's like 3.9 kilometers. Okay, what about vector B? We can do the same thing with vector B, right? We can break it into its x and y components. This one has a magnitude of 12 kilometers and a direction of 75 degrees. So we'll play the same game with vector B. Bx is magnitude B, cosine of the angle for vector B, for which we'll plug in 12 kilometers and cosine 75 degrees. So punch that into your calculator. And then for the y component, we'll have the magnitude times sine of the angle. So it's just the same exact idea, just applied now to vector B. So let's just see what we get for these two results. What do we get for the x component of vector b?
3.1.
So that's 3.1 kilometers. And what do we get for the y component of vector b?
11.6.
All right. So now do you see how we could just add these together now that we have all the x and the y components? Because remember, my resultant vector is what I get when I add a and b together. So let's remember how this works. I basically, to get the x component of my resultant vector, I'm just adding these two x components together. To get my y component, I'm just adding these two y components together, right? So I could just say, to write vector ax, we have 14.5 kilometers I hat plus 3.9 kilometers j hat. So the units actually have to come along when we write this out. Then I'm adding that to vector b, which, like I showed you before, I'm going to put on the next line, so you can see how the x components line up and the y components line up. So what do we have? We have 3.1 kilometers I hat, and then we have 11.6 kilometers j hat. So now you can do a straight calculation of the sum to get the overall x component here, and to get the overall y component here. So tell me, what is the overall x component? That's what we get when we take 14 and a half.
17.6.
Yeah, so that's going to be 17.6 kilometers. We'll round that off later, but right now I'm just going to write it as 17.6. And then what about for the y component? Add these two together.
15.5.
Yeah, so that's 15.5. So basically, what you just found here is Rx, and what you found here is Ry. You have the resultant vector in xy form. So the last step, which you should do at your desk, is to find the magnitude and the direction of this resultant vector. Okay? So take a few minutes to work that out. Make sure this is Monday. All right. Does anyone have the magnitude?
23.5.
Yeah. So here, let's actually do this real quick. So we agree this is Rx, this is Ry. If I want the magnitude of R, what I do is I take the square root of the x component squared plus the y component squared. So I know what's going into this formula. I'm not even going to write it out, right? I'm doing 17.6 squared plus 15.5 squared under the radical. And you end up with about 23 kilometers. We agree?
Yes.
Okay. We also know that tangent of my angle theta, which I'm trying to figure out what angle this resultant vector is pointing at, is equal to what again? I have tangent theta equals, just as a formula.
88.
So what I'm looking for is ry over rx, right? And then we'll put in the specific numbers. But first we have to take the inverse tangent, right? Okay, now I have to take a look at what I came up with before. What quadrant are we working in right here?
First one.
Yeah, we're in the first quadrant. I'll just write Q1 right there, okay? So because we're in the first quadrant, do I have to add anything to this?
No.
It's good as is. So in your calculator, type in inverse tangent of 15.5 divided by 17.6, and what do you get?
41.
41 degrees, okay? So remember when we did this the other way, by making a diagram and carefully measuring it, everything? I told you to write down what we got. What did we get last time? On Tuesday. So these two results.
That's 42 degrees.
Yeah, we got 42 degrees off the diagram, and then what for the magnitude?
24
Yeah, so again, it's pretty close. It wasn't drawn perfectly, and I didn't have graph paper. That could have helped a little bit. But hopefully you see that we're getting the same results within some minor error. All right, good on this? So now you know how to add vectors in multiple different ways. So what we're going to do for the rest of this lecture is just try to build up to more intricate examples of when we can take the sum of vectors and maybe see some applications for it. All right, so this gets us to directions on the map. So if you started doing the homework that's due next week, you'll already have seen some of this. Just want to be clear what it means when you see a statement like the following. Okay, so in a problem, you might see something like this. John is driving 35 meters per second at 30 degrees south of east. So let's be clear about what this little part means, south of east. So first of all, we have our cardinal directions, north, east, south, and west. And they line up very nicely with how we typically set up an x and y coordinate system. So like, what direction would east typically correspond to, the way we set up our x and y axes? Yeah, so east is like the positive x direction, and then north is like the positive y direction. That's just by convention, right? Okay, so if we're going 30 degrees south of east, what that means is we start here facing east, okay? And then once we start here, we just go 30 degrees south from that starting point. So we end up with this vector. Does that make sense? So 30 degrees south of east is this. I could have put that a different way and still arrived at the same vector. For example, if I said I want to go 60 degrees east of south, that means I start here at south, and then I just go east from that starting point, but this time by 60 degrees. And you see that I end up in the same exact orientation, right? So there's more than one way to specify a direction on a map, is the point of this. And just get used to being a little flexible with the way things are worded. All right? So do we have any questions on this? Okay. So let's do a few problems that utilize this sort of language. All right, so this one's a bit tricky. So follow along. Here's what's going on in this example problem. We basically have two people and a lung, just sort of situated at different places. So Bob is located 100 meters away from Alice in the direction 30 degrees north of east. So what does that mean? That means if Alice was to look out and see where Bob is, she would be looking in a direction 30 degrees north of east. That's what we mean, okay? Alice then looks out and she sees a llama, and she sees that off in a direction 40 degrees north of east, all right? But then Bob looks out, he sees that same llama, but he says that it's in a direction 50 degrees north of east. So how far away is the llama from Alice is the question, okay? So we have these three different locations on a map, basically. This is what's going on. We have the location of Alice, we have the location of Bob, and we have the location of the llama. And we get some sense of how these locations relate to each other, right? But what we're going to do is draw a diagram, because this might just look like a bunch of nonsense words. We'll put it on a diagram, and then hopefully you'll see what's going on here. And then we'll see how we can actually use vectors to answer the question, okay? So we good on this? So let's get to the picture, okay? So in my picture, I'm going to start by drawing the x and the y-axis. So we'll work within this coordinate system where this is my y-axis and this is my x-axis. And like I said earlier, y is pointing in the direction that we typically associate with north, and x as east. The way we typically read in math, it's oriented this way, right? Okay, so I'm going to start by putting Alice at the origin. It doesn't really matter where I put Alice, as long as I put everywhere else, every other point in the correct orientation relative to Alice, okay? So what do we know about Bob's location? Well, we know Bob is 100 meters away from Alice, and we know Bob is off in a direction 30 degrees north of east. So let's first think about what north of east even means. North of east means you start here, and then you go 30 degrees north from there. So I want to show that Bob is off in this direction at 30 degrees. So that looks like maybe this is Bob's location. Okay? And what I'm going to do next is I'm going to draw a vector which goes from Alice to Bob. Okay? And I'm going to call this vector AB. Makes sense, right? It's the vector that takes me from Alice to Bob. All right. Now, the other piece of information we were given is that Alice, she looks in a different direction, 40 degrees north of east, and she sees a llama off in that direction. So now let's go 40 degrees north of east, which is a little bit more than this. And then we'll just say that off here somewhere is point L, where this llama is located. Okay? And I can draw a vector going from Alice to the llama, which I'll call AL. All right? Let's actually indicate a couple different angles at this point. This angle is going to be 30 degrees. That's the Alice to Bob vector. That's oriented at 30 degrees, right? And then this one, which goes from Alice to the llama, that one's at 40 degrees. We see that? Okay. And then finally, there's a vector that goes from Bob to the llama, this one. We're told that this one is at 50 degrees. Okay? Because what we're told is that Bob looks off in a direction 50 degrees north of east, and that's the direction he has to look to see the llama. So does it make sense that this is how we would set up the diagram of just the locations of everything in this problem? Okay. The last thing I want to do is label this vector BL that I just drew, okay? Do you notice something going on with these three vectors? Does it look kind of familiar the way they are organized?
They form a triangle?
Yeah, they do form a triangle, but beyond that, they're showing us a vector addition. You see this? AB is tip to tail with BL. This vector is tip to tail with this one. And then this vector is the resultant that I get when I add these two together. Right? Because these two are connected tip to tail, and this vector starts at my first vector and ends at my last vector. So, kind of subtly, what's being shown in the diagram is a vector addition. So the diagram shows the following. We have AL is equal to AB plus BL. It probably would be hard to see that unless we just drew it out like this, right? But now that we've drawn it, we can solve for what we want. So let's talk about what's known. What quantities in this problem do we know? Well, we know the distance between Alice and Bob, right? That would be the magnitude of my vector AB. That's the 100-meter distance that we're given, okay? Does that make sense what I just said? The distance between Alice and Bob is the length of this vector, and that's 100 meters. We know that. We also know some angles, don't we? Mm-hmm. We know the angle of my vector AB off the x-axis, which is 30 degrees. We know all the angles, in fact. We know the angle of my vector AL, which is 40 degrees off the x-axis, and we also know the angle of the vector BL, which is 50 degrees off the x-axis, okay? So, with those as our knowns, what are the unknowns? Well, we know all three angles for all the vectors, but we only know one magnitude. So there are two magnitudes which are unknown. Does that make sense? What are the unknown magnitudes? Yeah, BL and AL are both unknown magnitudes. So we don't know either of them. So that might seem like a problem initially because, I mean, I wrote down one equation, right? And I'm saying I have two unknowns. Don't I need two equations to solve for two unknowns? That's how it works, right? Does anyone see the solution to this? Okay, the solution is, this equation I wrote down, it's actually two equations in disguise. There's an equation for the x direction, and then there's a separate equation for the y direction. And that's actually how we have two equations, two unknowns in this situation, okay? So let me explain what I mean. Let's break this down by component. Which gives me an x equation, which I'll write this way. Okay, AL, if I just pick out its x component, that should equal AB, just picking out its x component, plus BL, just picking out its x component. So if it's really true that this vector equals that vector plus that vector, it should be true for the x component, right? And it should also separately be true for the y component. Otherwise, this equation isn't even true, okay? So now let's put some numbers into this, okay? So I have this vector AL right here. Just generally speaking, how do I write down the x component of any vector? If I know its magnitude and its angle, how does that go?
You have to do the magnitude of A, or the magnitude of the vector times the cosine of the angle?
Exactly. So, okay, see what I have here? I have AL, just the x component. So that's the magnitude of AL, which I don't know, so I'm going to have to keep this as an unknown. but it's multiplied by cosine of the angle for this vector, which is 40. Cosine of 40 degrees. Okay? So that's just this side of the equation. But that should equal ABX plus BLX. So in other words, I'm going to write down the x component of each one of these also. Okay, for the x component of AB, I would be taking the magnitude, which is actually 100 meters. So we know that, so I'm going to insert an actual number there. And then cosine of this angle, which is 30 degrees. So that's just the x component of vector AB. It's just 100 meters cosine 30 degrees. Okay, and then finally I have this. I have the x component of vector BL, which would be the magnitude of that vector. We don't know what it is, so I'm leaving that as unknown. And then we take cosine of the angle, which is 50 degrees for this vector. Okay? Does that make sense what I just did? I'm just saying the x components have to follow our original equation. And I wrote out exactly what the x components are. I put in numbers where I could, and then where I didn't know the value, I left it as an unknown. Okay? So we could do the same thing for the y components, couldn't we? Which is just saying, AL y component equals AB y component plus BL y component. All right? And you know what? Let me just show you on the diagram to go into some more detail about what this is saying, okay? If I take AB and I take its y component, that's how this AB vector projects onto the y-axis. So you see how this distance right here is ABY? And then same with BLY, like that's just how this vector projects onto the y-axis. That would be this length over here. So that actually equals, if you look at the diagram, ALY, which is how our final vector projects onto the axis. So all this equation is saying is, this y component plus this y component gives us our resultant y component. That's the way to visualize it. But anyway, back to the equation, okay? Okay, I have AL y component. That's going to be the magnitude of AL times what exactly? Sine of the angle associated with this vector, which is what? 40 degrees. Okay, then I have ABY. That's going to be magnitude of AB, which is 100 meters. We said that already. And then I'll take the sine of the angle associated with that vector, which is 30 degrees. And then I'll take, for this last one, the magnitude of BL times cosine, sorry, what am I saying? Sine of 50 degrees. Okay? So I have two equations here. An x equation and a y equation. And I have two unknowns. There's some algebra to do after this, but I think the hard part is actually just setting this up. Okay? So I don't know if we have enough time to just crank out the algebra. So I'm going to show you what the answer is, right? I have these two equations. You could try, subbing out one of the variables in one equation, plugging that into the other to get your final answer. But let me just give you the result, okay? If you solve this set of equations, you'll get magnitude AL equaling 197 meters. And you'll get magnitude BL equaling about 100 meters. And this is the answer we want. We want to know how far Alice is from the llama. So it's 197 meters. All right? So any questions just on how we set this all up? Anything?
If the degree was from, in between the triangle, not on the outside, would we still be able to use that angle? on the inside instead of on the front for the line?
Yeah. Yeah, here,
Yeah, if it was on the inside, would it still be able to use?
like this angle.
Yeah.
So in order to say that the x component is magnitude times cosine of the angle, and the y component is the magnitude times sine of the angle, it has to be measured off the x-axis for that to work. So we have to make sure we're going off the x-axis, which is this 50-degree angle. If you don't have that angle, it's like if you had this one instead, you could figure out through geometry what the angle you want is actually going to be. So we'll see some examples of that coming up, I think. Anything else? Okay, so that was kind of a tough one. Let's do another one. This one's probably a little more straightforward. We have two ropes that are tied to the top of a flexible pole, and that pole is placed in the ground. So in this picture, you're seeing a top-down view. So the pole is like coming out this way. So we have the first rope being pulled with a force F1, which has a magnitude of 18 newtons. Okay, so force is measured in units of newtons. We don't need to know what a newton is yet. We just want to do a calculation. We'll get to this in a couple chapters, okay, what a newton actually means. The second rope is being pulled with a force that has a magnitude of 12 newtons. So that's this one over here. And also see that you're given the direction of each one of these forces, okay? So one of them is 30 degrees going this way, the other is 45 degrees going that way. So the question is, suppose we had a third rope that we attached to the pole. How hard would we have to pull that? So what would the force be? And in what direction would that force have to be in order for the total force to go to zero? So you see how if you had these two forces, the pole would kind of flex this way, right? But if I were to balance it out with another pole going down this way, I could get it to all balance out, right? That's what we're trying to find. So now we have a third force, let's call it F3, so that if I take F1 plus F2 plus F3, I get exactly 0. That's what I'm trying to find. What force would I have to add to these two to give me 0 for the total? Does that make sense? Okay, so let's work it out. So the problem, if we state it as an equation, is we have three forces, F1, F2, which are shown on the diagram, and then there's some unknown F3, which I'm trying to work out, which when we add them all together equals 0. Okay? And the one that I'm looking for is F3. So how do I take this equation and solve for F3? Just add the other two forces to the other side, right? So what does that look like when I do that? So it's minus F1 minus F2, right? That's what I'm saying. All right, so what are we given here? Let's write this out. What are we given? We're given the magnitude of F1. In the problem, that was 18 newtons. That's how hard we're pulling on the first row. We're also given the angle for that first one. This is 30 degrees off the x-axis. Okay? Off the positive x-axis, I should say. What about F2? This one had a magnitude of 12 newtons. And what about the angle? Let's actually just do a quick sketch of this. To remind you what this looks like, F2 was off over here, and we were given that this angle was 45 degrees. Okay? But what I want is the angle going this way off the positive x-axis. Right? If we have xy like this, the standard way to measure the angle is to start at the positive x-axis and then go counterclockwise from there. So what should I say my second angle is in that standard way of measuring it. Yeah, so here, this is the angle I want. This is the angle I have. The one I want is just 180 minus this one, right? The angle I want is 180 minus 45, which, as you said, is 135. This is actually 0.0, so I'll write this 135.0 degrees. Okay? So this is how you deal with it if you're given an angle that's not in that standard format. Okay? So I think we're ready to go. Basically, I'm adding these two vectors together, which is minus f1 and minus f2. And each one, I'm just going to express in xy component form, because that's how you generally do this. So what we have is f3 equals, okay, I'm going to put a negative sign out front for f1. And then I'm going to write f1 in xy form, okay? So how does this work? For the x component, I have 18 newtons times cosine of 30 degrees. That's the x component of that first vector. Then I'll write an I hat unit vector, so we know I'm talking about the x component. And then I'll write the y component, which is 18 newtons, sine of 30 degrees, j hat, like this. But then I'm going to take minus f2 as well, and I'm going to write f2 in xy form. So I have 12.0 newtons. I have cosine of 135 degrees, because this one is in the second quadrant. We had to make sure our angle is expressed correctly. And then I have 12 newtons sine of 135 degrees for the y component of that vector. So basically, to get the x and y components of vector f3, here's what I'm doing. I'm taking minus 18 newtons times cosine 30, and then minus 12 newtons cosine 135. And that will give me the x component for f3. Just add all this together, right? Then, for the y component, I would take minus 18 sine of 30 degrees, and then minus 12 sine of 135 degrees. And then that would give me the y component I'm looking for. So, someone just try doing those computations. Like, what do we get for the x component? Doing this addition right here. Make sure there's a negative sign in front of each term.
Negative 7.7? Negative 7?
All right, this is minus 7.10, right? Newtons. And then what about for the y component? Just do the same thing except switch cosine with sine. Yeah, so this is like minus 17.5 newtons. Now this vector is in which quadrant? That's in quadrant 3. It makes sense that it would be in either 3 or 4. We know it has to be pulling down, right? So if we ended up with an answer that was in quadrant like 1 or 2, you know there was a mistake. So I'm just writing this down as just a basic check, all right? So if I want the magnitude of this guy, then I'm going to take the square root of minus 7.10 newtons, and I'm going to square that. That's the x component squared, plus minus 17.5 newtons, and I'll square that, and then I'll get my answer. What's the answer for the magnitude?
18.8?
Yeah, so 18.8 newtons. That's how hard you have to pull this. Okay, that's a measure of the force. Okay? But then, in what direction do we have to pull? That's an angle now, right? So, that angle I'll call theta 3. And we know how this works by now. If we take the inverse tangent of this y component divided by this x component, but then since I'm in quadrant 3, if I want to end up with an angle that's off the x-axis, what would I do to this? Then I would add 180. So I just want this to come out for our purposes as an angle, some number of degrees off the positive x-axis. So when you do this calculation, what do you get? 248, right? Degrees. So in order to cancel out the other two forces, you have to pull with this amount of force at this angle. Any questions? All right. Let's keep going then. So we've covered all the content that I wanted to cover, but since we have about 12 minutes, I want to go through one more example. I think it'll be useful, okay? So as you know, the practice problems at the end of each lecture, you can find the answers to these on Canvas under the lectures folder. So this is going to be useful for like studying for the test. We're just going to get through one today, but there are a whole bunch of others. So when you're studying for the test and quizzes, you can use these. But let's just do the very first one. This is another one that involves directions on the map. So I think this will be a good one to go over. So you go on a long hike by first walking in a straight line from your car for 25 kilometers in a direction 45 degrees south of east. You then stop and camp for the night. On the second day, you walk in a straight line from your campsite for 40 kilometers in a direction 60 degrees north of east. So when you're finished walking, how far away from your starting point are you? Just straight line distance, how far away? And then as a follow-up, in what direction are you relative to your starting point? Okay, so we're going to find basically a magnitude and a direction here. Okay, so in a problem like this, what we want to start with is a picture. Let's put a picture down on the diagram, and that will inform us as to what calculation we need to do. Okay, so the picture is going to look something like this. Because we have directions on the map, I'm going to start by drawing a y-axis corresponding to north and an x-axis corresponding to east, okay? And I'm going to put at the origin your starting point. So we start here. So we head in a direction 45 degrees south of east, okay? What does that mean? It means we're starting. If we want to measure the direction, start here, pointing east, and then go 45 degrees south from there. That's what that means. So the first vector is going to be pointing like this. And it's going to take us to our campsite. So this is the car, this is the campsite. The vector that takes us there is going 45 degrees south of east. Okay? And I'm going to call that vector R1. Okay? Then the next thing we do is we walk in a direction 60 degrees north of east. So what that means is, as far as the direction we're headed, we think of a vector starting like this, but then going 60 degrees north from there. So 60 degrees north of east means we start east, 60 degrees north from there. So something like this. And I'll show you the 60-degree angle. Let's call this second vector R2. This takes us to our endpoint. So these are the two motions that I undergo, right? And this vector right here is just a straight line from my car to my endpoint. And that's what I want to know about. I want to know how far apart these 2 points in space are, right? I also want to know what the direction is. Okay? So I'll call this angle right here some kind of unknown theta. Got it? Here's what we know. The magnitude of vector R1 is just how far I walked from the car to the campsite. That was 25 kilometers. Okay, for this first vector R1, there's an angle that we could definitely specify, right? How should I denote the angle here?
360 minus 45.
Yeah, so here, let me explain what I mean. What I actually want is this angle, which goes from the positive x-axis all the way around to this vector. So that would be 360 minus 45, because you have 360 and 45 adding, or you have this angle and 45 adding to 360, and that gives you 315 degrees. Okay? And then for the second vector, the magnitude is 40 kilometers. That's just what we were given. That's how far you walk for that second leg of the journey. And what should we say about the angle for that second vector? It's already in the right direction. In other words, we're going off the x-axis, going counterclockwise. It's in the first quadrant, right, at 60 degrees. So that's fine. Does that make sense? Another way I could have done the angle here, by the way, is I could say minus 45 degrees. Right? Because we're just going in the opposite direction that we typically measure the angle. So minus 45 degrees would also work here. Okay. So this vector that takes me from the car to the endpoint, I'm going to call that R total. And as we can see from the diagram, R total is equal to R1 plus R2, right? Because I'm taking R1 and R2 tip to tail, and that's giving me R total. Does that make sense? Okay, so if I'm adding 2 vectors together, I'm going to break each one into x, y components. My first vector is 25 kilometers cosine 315 degrees I hat plus 25 kilometers sine of 315 degrees j hat. Okay, my second vector, that's the one with a magnitude of 40 and a direction of 60. If I write that in xy form, is 40 kilometers cosine of 60 degrees I hat plus 40 kilometers sine of 60 degrees j hat. Okay, so those are my 2 vectors added together. And what I want is the resultant of this. Okay, so if I want to get my overall x component, what I'm adding are these 2 numbers together. Okay, we're running out of time, so I'll just tell you what it is. Follow along in your calculator if you like, but this comes out to 37.68 kilometers, which we'd round to 3 sig figs. Okay. When we add the y components together, adding these 2 numbers together, what you'll get is 16.96 kilometers. So my distance between the car and the endpoint is the magnitude of this vector R total, because I just want to know how long it is, basically. And that's going to give me the square root of 37.68 kilometers squared plus 16.96 kilometers, square that. And if you punch this into your calculator, here's what you end up with. 41.3 kilometers. So that's the distance between your starting point and your end point. the direction that you have to go in to get straight from your starting point to your end point, which we're calling theta right here, is just the angle of our resultant vector. So what we do for that is we take the inverse tangent of this y component divided by this x component. That's generally how this works. So we have 16.96 over 37.68. Take the inverse tangent of that, and what you get is 24.2 degrees, measured this way. Okay? So using our directions on the map, we can say that it's 24.2 degrees north of east. Okay, that's how you do this one. So it was a little rushed because we had to finish up, but I'll leave this up here, and then we'll wrap up class, and I'll see you in lab. If you have lab today, if not, I'll see you next week.